Imagine you want to train a state-of-the-art image generator, but the price of admission is hundreds of GPU days and a carbon footprint to match. That was the reality of diffusion models in 2021. They produced gorgeous images, but they did all their thinking pixel by pixel, which meant every training step and every sample required wrestling with data in its rawest, highest dimensional form. This paper, which introduced what we now call latent diffusion models, asked a simple question. Do we really need to do the expensive part of generation in pixel space at all? To set the stage, let's recall what a diffusion model actually does. You take a clean image, gradually add noise until it becomes pure static, and then you train a neural network, usually a UNet, to reverse that process step by step. Generate a sample by starting from noise and running the denoiser many times. The math is elegant and the results are gorgeous, but each of those denoising steps has to evaluate a network over every pixel of a high-resolution image. Training the best models at the time burned somewhere between 150 and 1,000 V100 GPU days, and even generating 50,000 samples afterward could take 5 days on a top-tier GPU. Now, prior work had already noticed something important about image generation. Most of the bits in a digital image encode imperceptible texture and noise, not the meaningful content. Think of it like an audio recording where most of the data describes the exact waveform shape of background hiss rather than the melody. Likelihood-based models, including diffusion models, are mode covering, so they dutifully spend capacity modeling all that perceptually irrelevant detail. To sidestep this, researchers had built two-stage systems like VQVAE and VQGN, where you first compress images into a discrete codebook and then train an autoregressive transformer over those codes. The problem is that to make the transformer tractable, you had to compress aggressively, and that aggressive compression threw away detail that you could never recover. You were stuck between a transformer that couldn't scale and reconstructions that looked blurry or warped. The key insight of this paper is that diffusion models are a much better fit for a moderately compressed latent space than transformers are. Because the UNet backbone has strong spatial inductive biases, it doesn't need the latents flattened into a one-dimensional sequence, and it doesn't need brutal compression to be efficient. So the authors propose a clean separation of labor. First, train a perceptual autoencoder once. It encodes a 512 by 512 image down to a latent grid that's perhaps 4 or 8 times smaller in each spatial dimension, and a decoder reconstructs the image. This autoencoder is trained with a perceptual loss plus a patch-based adversarial loss, which keeps reconstructions sharp and faithful, and the latent space is regularized either with a mild Kullback-Leibler penalty toward a standard normal, or with vector quantization absorbed into the decoder. Then, with that autoencoder frozen, you train a standard diffusion model entirely in this latent space. The UNet now denoises latent tensors rather than pixel tensors, which is dramatically cheaper. And at sampling time, you just run the diffusion process in latent space and decode the final result once. The other major contribution is how they handle conditioning, meaning how you tell the model what to generate. They inject conditioning information, whether text, semantic maps, or class labels, through cross-attention layers added throughout the UNet. A domain-specific encoder, like a transformer for text prompts, turns the conditioning input into a sequence of tokens. Then inside the UNet, the spatial features become queries while the conditioning tokens become keys and values, so each spatial location can attend to the relevant parts of the prompt. This is the same cross-attention mechanism that powers translation models, but here it bridges modalities, letting language directly steer image synthesis. The beauty is that this is general purpose. You train the autoencoder once, then you can spin up different conditional diffusion models on top for text to image, layout to image, super resolution, inpainting, and so on. A lot of the paper is really an empirical study of the sweet spot in compression. They sweep down sampling factors from 1, meaning no compression, up to 32, which is very aggressive. Downsampling factors of 1 or 2 barely help because the diffusion model still has to chew through huge tensors. Downsampling by 32 throws away too much information and the achievable quality plateaus. Factors of 4 and 8 hit a near optimal balance, where the autoencoder handles the perceptual compression of imperceptible texture, and the diffusion model focuses its capacity on semantic structure. The numbers back this up. On ImageNet class-conditional generation, their model reaches a Frechet inception distance of 3.60 with classifier-free guidance, beating the previous best diffusion model ADM while using fewer parameters and roughly a quarter of the training compute. On Celeb AHQ, they hit 5.11 FID, a new state-of-the-art at the time. For text-to-image on MS Coco, their 1.45 billion parameter model is competitive with much larger autoregressive systems like Make a Scene and Glide that have several billion parameters. They also set new state-of-the-art results for image inpainting on places, and showed that because the diffusion UNet is fully convolutional, a model trained at 256 by 256 can be run convolutionally to generate consistent megapixel images for tasks like semantic synthesis. Now for the honest limitations. Sampling is still sequential and still slower than a single forward pass through a GAN. The autoencoder is a hard floor on quality. Anything it can't reconstruct, the diffusion model can't generate. So for tasks demanding pixel-perfect fidelity, like certain medical or scientific imaging, the F equals 4 reconstruction error might be a real bottleneck. The authors also acknowledge significant societal concerns. These models make manipulated imagery and deepfakes much cheaper to produce. They can leak training data, and they inherit biases from web-scale datasets like Leon 400M. Looking forward, the impact of this paper has been enormous. The Stable Diffusion family is essentially this architecture scaled up, and the combination of a pre-trained autoencoder plus a latent diffusion UNet with cross-attention conditioning has become the default recipe for open-source generative imagery, video, and even audio. Now let's walk through some questions you might have after hearing all of this. The first one people usually ask is, why does training in latent space work so much better than the aggressive compression that VQGAN plus a transformer used? The answer comes down to inductive bias. A transformer over a one-dimensional sequence of code tokens has no built-in notion that nearby tokens correspond to nearby pixels. So to make the sequence length manageable, you have to compress hard, and that hard compression destroys detail. A diffusion UNet operates on the latent as a two-dimensional grid with convolutions and spatial attention. So it natively understands spatial structure and can work efficiently on mildly compressed latents that preserve far more detail. Another natural question is, doesn't training a separate autoencoder first create a quality ceiling that the diffusion model can never escape? Yes, and the authors are upfront about it. Whatever the decoder can't reconstruct from the latent is lost forever. But they chose their compression rate specifically so that reconstruction is nearly indistinguishable from the original to human eyes, with peak signal-to-noise ratios well above competing approaches like Dolly's discrete VAE. The trade is that you accept a tiny, often imperceptible quality ceiling in exchange for an order of magnitude speed-up in training and inference. A third question worth dwelling on is, why use cross-attention for conditioning instead of just concatenating the conditioning information to the input? Concatenation works fine when the conditioning is spatially aligned with the image, like a low-resolution image for super-resolution or a semantic segmentation map, and the paper does use concatenation in those cases. But text prompts have no spatial structure. A caption like, "A squirrel eating a burger," needs to be able to influence every spatial location, and different words need to influence different regions. Cross-attention lets each spatial query in the UNet pull in whichever text tokens are most relevant, which is exactly the flexibility you need for modality bridging. So how does this translate to large-scale recommendation systems? The core lesson that you should do expensive generative or representational work in a compressed semantic space rather than over raw high-dimensional inputs maps almost directly onto industrial recommender architectures. Think about user modeling at platform scale. You have billions of users, each with long, sparse, high-dimensional interaction histories. Running expensive sequence models or generative retrievers over raw interaction logs is prohibitive. The Latent Diffusion playbook suggests training a strong autoencoder once over user histories or item content, then doing your generative ranking, candidate synthesis, or counterfactual user modeling entirely in that compact, latent space. The cross-attention conditioning trick is also directly relevant. For multimodal item understanding, where you want to fuse text, image, and behavioral signals into a unified item representation, cross-attention between a frozen content encoder and a behavioral tower gives you a flexible, trainable bridge without rebuilding the whole stack. More concretely, generative retrieval is becoming a real production paradigm, where instead of an approximate nearest neighbor search over item embeddings, you train a model to generate item identifiers conditioned on user context. The latent diffusion lesson here is that you don't want to generate over raw item IDs in a giant vocabulary. You want a learned, structured latent space for items, possibly trained with the same perceptual loss plus adversarial loss recipe adapted to behavioral data, and then run your conditional generative model in that space. This gives you faster training, faster inference, and the same kind of clean separation between representation learning and conditional generation that has made latent diffusion the dominant paradigm in images.